This is my Physics 2211 Lab 2 about motion of a falling object. So the goal of this lab is to observe an object, in this case a ball of paper, falling straight down from rest, to perform a tracker analysis on that ball's position over time, and then create two computational models, both predicting motion of a falling object, but one accounting for drag and the other not. And in this case, we're assuming the net force is always in the y direction, and acceleration due to gravity is 9.8 meters per second squared. A couple of essential concepts include Newton's second law, where the net force on object equals its mass times its acceleration, and the position and velocity update formulas, which given initial values such as average velocity and initial velocity, can determine the final position, final velocity. Additionally, gravity on Earth's surface is equal to 9.8 meters per second squared. The force of gravity is an object's mass times its acceleration, and then the law of universal gravitation, as seen below, can be rearranged to give you acceleration due to gravity on Earth's surface. So we look at the system. There's three free body diagrams shown here. The first one shows when an object is simply falling without accounting for drag, so like in a vacuum, where the only force is the force of gravity. The second and third free body diagrams account for the force of drag, but the second free body diagram shows shortly after being dropped from rest, while the third one shows a longer time period after being dropped. And you can see that as the ball's or object's velocity increases, so does the force of drag. And this is because that the equation for drag force is a proportionality constant times velocity squared. So its growth is exponential as velocity increases. Here's the video of the paper ball being dropped, relatively straight motion, and here's the tracker analysis of that falling object. And as you can see there, it followed the position as it dropped and created data points for position over time. In this case, when I did the tracker analysis, the video frames per second was 30, so every single time step was a 30th of a second. And I measured the paper ball mass to be 0.005 kilograms or 5 grams, but this does not pertain to the lab, as mass does not affect the calculations or anything in this lab, even though it does impact force of gravity, but not acceleration due to gravity. The total interval was 0.6 seconds long, and the initial velocity was 0 as it started from rest, and then the final position was negative 1.68 meters relative to where it started. In this first computation analysis, you can see that I set the proportionality constant of drag equal to 0, so it doesn't account for it. That time step equal to a 30th of a second. And in this data here, I use the position and update formulas in the code by using fnet and the time step being delta t. In this case, I did account for drag, and you can see that I made a proportionality constant found just by testing random numbers until it closely matched the experimental data. And you can see here that I set fnet equal to the force of gravity plus the force of drag, and then divided the net force by mass in both the velocity and position update formulas to find acceleration. And when I combined the tracker and the two computational experiment data into one large graph, you can see that the computational data that involved drag closely matched that of the experimental data, whereas the computational model that didn't involve drag was diverged from them as time went on, which was expected as I modeled the proportionality constant after the experimental data. All three models demonstrate acceleration that changes velocity over time, and the model that did not account for drag was significantly different, assuming a farther distance traveled, which makes sense because it didn't account for a force opposing gravity. And there are a couple sources of error, such as simply human error in placing the center of mass in the ball with motion blur, and also estimating the drag coefficient, as this was completely random and just choosing a number that seemed to fit well. So here we ask, what does it mean in terms of terminal velocity, which is where the force of drag and force of gravity are equal, so there's no acceleration. And we could see that the model that predicts drag will result in a prediction of terminal velocity, whereas the one that doesn't will not, which makes sense because terminal velocity depends entirely upon the existence of drag. And as you can see in the graphs below, on the left, the one that involved drag, velocity levels off, whereas the one on the right that didn't predict drag, it does not level off. And here we also ask what if the ball was initially thrown downward. Because the terminal velocity is a constant when the drag force equals the force of gravity, there is no change that due to throwing it originally. As you can see here, they level off at around 5.7, 5.8 meters per second squared downward, meaning that the initial velocity had no impact. It would just meant that it would reach the terminal velocity faster.